Assalamualaikum and greetings our beloved lecturer Dr. Aina Awanis binti Muhammad Badia Zaman. I am Wanas Linda binti Wan Muhammad Hanafiah from AS1205H. For today, we would like to present about experiment 6, which is high performance liquid chromatography HPLC in caffeine. Before we start, I would like to introduce first my group mates. So we have Nurin Batrisha, Ain Ashikin, Muhammad Haikal and also Muhammad Haris. In this video presentation, it contains introduction, objective, methodology, result and discussion, and also conclusion.
Welcome to this introduction to high performance liquid chromatography or HPLC. In this video, we explore what HPLC is, how it works, and why it's an essential tool in model analytical science. HPLC stands for high performance liquid chromatography. It's a technique used to separate, identify, and quantify components in a mixture. It plays a crucial role in analyzing complex samples with precision and accuracy. HPLC operates by distributing analytes between two phases, a mobile phase, which is a liquid solvent, and a stationary phase, typically packed material in a column. High pressure is applied to move the mobile phase through the column, enabling efficient separation. One of the defining features of HPLC is its ability to achieve high-resolution separation. This is due to the high pressure used, ensuring even minute differences in sample component can be analyzed. HPLC is widely used across industries. In pharmaceutical, it ensures the quality and consistency of drug. In food production, it monitors safety and quality. And in environmental science, it helps detect pollution with remarkable sensitivity. High-performance liquid chromatography is a cornerstone of modern analytical method. Its precision and versatility make it indispensable in research, quality control, and diagnostics.
So the objective of this experiment is to determine the retention times of standard solution, which are caffeine. Next, to identify the caffeine peak in a soft drink sample. And lastly is to determine the amount of caffeine in soft drink sample using the response factor method.
So first, let's take a look for the HPLC component. HPLC component will work together to separate and quantify the metformin from a sample. First, it will start at the mobile phase that will go into the solvent delivery pump, which is known to push the solvent. So, the sample will be transported through the column that we also know as a stationary phase. In the column, it will separate the mixture component. So, the component will be sent to the detector to detect the metformin and generate the chromatogram, and finally the data system will be analyzed to the result. In addition, let's learn about a principle of HPLC. First, we got a mobile phase. It is a liquid solvent or mixture of the solvent. Next is pump. It delivers the solvent to the column. So, column is a stationary phase that typically solid material. So next, we got a separation based on differential affinity. It is separate component of a mixture based on different interaction. Next, we got a separation efficiency. It provides high resolution and efficiency in a separate complex mixture. Lastly, we got a differential elution. It is a different component with different degrees interaction. So last but not least, we got a detector. Detector will convert the amount of the component into an electrical signal.
Next is results and calculations. First, let's take a look at the chromatogram shown here. So this chromatogram illustrates the retention time of the caffeine peak in the standard caffeine, which is recorded at 2.482 minutes, and the peak area was measured to be 6249.48779. Next, we utilize this data to determine the concentration of caffeine in the unknown sample using the following formula. First, we calculate the response factor, which is the formula is response factor is equal to peak area of the caffeine standard divided by the concentration of the caffeine standard. And next, we can determine the concentration of caffeine in the sample. by using the formula of concentration is equal to peak area of caffeine in the sample divided by the response factor. So through these calculations, we were able to analyze and quantify the caffeine content in the unknown sample effectively. So let's start by analyzing the caffeine content in Coke. From the chromatogram, the retention time for caffeine is recorded at 2.481 minutes, which matches to the standard caffeine's retention time. And the peak area for caffeine in Coke is 7001.12305. By using the response factor, we can calculate the concentration of caffeine by dividing the peak area of caffeine in Coke and the response factor. And then the outcome is 1.12027 mg per mil. And lastly, the concentration is times with 1000 ppm per 1 mg per mil to get the final result in ppm unit. So the caffeine concentration in Coke is approximately 1.12027 times 10 to the power of 3 ppm. Next, let's move on to the caffeine content in Nivita. Here, the retention time for caffeine is recorded at 2.479 minutes, which is very close to the standard caffeine's retention time. And the peak area for the caffeine is 1.11511 times 10 to the power of 4. And by using the same response factor, which is 6249.48779 mg per mil, we can find the concentration of caffeine in Nivita by dividing the peak area of the caffeine in Nivita with the same response factor. And we got 1.11511 times 10 to the power of 4 mg per mil. So lastly, the concentration is times with 1000 ppm per 1 mg per mil also to get the final result in ppm unit. Thus, the caffeine concentration in Nivita is approximately 1.78432 times 10 to the power of 3 ppm.
The result highlight the retention times, peak areas, and calculated caffeine concentration in Coke and Nivita. The caffeine standard solution had a retention times of 2.482 minutes, confirming the accuracy of the method. Coke had a retention times of 2.481 minutes, which are a peak area of 7001.2305 and a caffeine concentration of 1.1202 times 10 to the power of 3 ppm. In comparison, Nivita show a slightly shorter retention times of 2.479 minutes, a peak area of 1.1511 times 10 to the power of 4, and a caffeine concentration of 1.7843 times 10 to the power of 3 ppm. These differences indicate higher caffeine levels in Nivita than in Coke, consistent with the expected formulation of energy drinks compared to soft drinks.
Back to me again. So this experiment successfully achieved its objective. The retention time of standard caffeine solution was determined to be 2.482 minutes, which closely matched the retention time of caffeine in Coke and Nivita. This consistency verified the reliability of Hplc in identifying caffeine. The caffeine contained in Nivita had a higher concentration than caffeine contained in Coke. These results demonstrated the effectiveness of the response factor method in quantifying caffeine concentrations in beverage samples. In summary, this experiment highlighted the precision and reliability of Hplc as an analytical tool for identifying and quantifying components in complex mixtures. It reinforced the importance of this technique in ensuring the quality and safety of consumer products. That's all from us. Thank you for listening and have a nice day.